Can you all see my slides? Is it visible to everyone?
Yes.
Yeah?
Yes. Yes.
Okay. So then, so we saw already this one. Let's move on. So there are a couple of things here to consider when it comes to electricity, and it's sometimes difficult to explain how crucial things can be with electricity, how unlike any other resource. So I'm sure all of you have been exposed enough to economics to have a feel of the supply and demand functions and what is really happening in most other domains. Yes, so you have demand of goods, you have supply of goods. Now the electricity demand is essentially each one of us when we start using electricity at our houses, when we switch on the light switch on an electrical appliance and so on. But there are also things like industrial uses and public lighting on the streets and transport, like the metro trains in the cities or other suburban, urban trains, commercial buildings, houses, like I said in the beginning, and so on. So these are your normal demand side aspects for electricity. There's the other side, which is completely different, of course, and that is and that is the supply. For a second, because I do get messages that are people in the lobby. I wish I knew how to do that. Oh God. Okay. Okay, so. Okay, hopefully I've managed to admit. Have I? Doesn't look like it works. Okay. Can you still see my slides or have I stopped sharing?
No, it's okay. It's okay.
Yeah, okay. Sorry, thank you. So let me go back here then. So supply is then the other side where we're thinking of electricity production. And when we're thinking of electricity production, that is typically power stations running on coal, gas, oil, nuclear, wind, solar, solar radiation, hydropower, geothermal, biomass, whatever. So there's a production of electricity side. And we bring these two together through cables. We connect supply and demand through cables. Now, it's extremely important to think specifically for electricity, the issue of timing. So timing is not a very easy aspect when it comes to electricity. And the reason is you need to be able to match supply with demand pretty much at all times. And there's very little room for flexibility there. Let me show you a little bit more on that. So typically, you will have things like base load power. So some part of the demand, if we start from that, some part of the electricity demand is typically what we would call the base load. That is electricity demand that is there pretty much at all times. So a degree of demand exists at all times. Why is that the case? What type of demand never switches off? What type of electricity consumption is always there, never switches off? Have a think.
For example, refrigerators, fridges.
Correct. These appliances are always there. And they're always there at an individual point of view. Yeah, if you're thinking of one refrigerator at your house that does not consume energy continuously, yeah, it switches on and off itself. It has a thermostat. When the temperature inside the fridge rises above a certain point, then the compressor behind the fridge starts working and it consumes electricity. But if you factor in, 1 million of fridges around the country, then the total consumption that they have at any given time, that is a type of consumption that never goes away. What else?
Life support.
Sorry, what?
life support machines, like medical machines?
Correct. Yeah, life support systems. Yes, these are also types of demand that never go away. Anything else?
Public lights.
Public lights, they do go away in daytime mostly. Yeah, is what you meant?
Maybe some kind of industries.
Correct. Some types of industries can actually do that. Yeah, it is true. Like, can you think a little bit? Do you have any ideas?
Food.
Say again?
Food.
Food industries. Not sure I've ever seen a food factory working 24/7. Maybe they exist. I don't know of any.
Cell towers.
Servers like cloud servers.
What was that? Say it again?
Cloud servers that supply like
cloud service, correct. So basically internet hosting services and stuff. Yeah.
Iron industry.
Yeah, what type of industry? No? Okay, so there are certain industrial processes which are known for their need to be continuously producing. There aren't that many. Most industrial processes are designed to shut down and start again. So that's to accommodate shifts, yes, so for employees to be able to come in and out. And very few types of production produce through the night and 24/7. It can happen, but it's not very common. Most industries don't work 24/7. There are, however, certain types of industries, and I'm thinking here production of cement is a typical one that should not be stopped. So normally it works from the beginning to the end. It's never ending. And there is also production in refineries. So oil refineries typically work non-stop. These are the two largest sectors that have non-stop production. So they would have a demand that is carrying on. There are also other types, like for example, in steel and aluminum production, you could have continuous production in certain places.
In paper,
again, these are processes that make more financial sense if you can carry on non-stop. Sorry, I thought somebody said something, I've missed it.
Yeah, sorry, yeah, if I interrupted you. Maybe paper too, maybe.
Paper, I haven't seen a paper mill working overnight, but to be honest, let's face it, I don't know every factory in the world, yeah? So the ones I have seen do close at nighttime.
Yeah, of course, okay.
But maybe others don't, I don't know. So again, there are then some processes, as you see, that need to carry on overnight and some others that don't. But even besides all of that, there are processes that during the evening hours, for example, they would increase their demand, yeah? So like somebody said before, lights, correct, use of lights, street lighting and household lighting, all of these are types of consumption that just grow overnight. And they don't exist over the day. So, or at least they exist at a much lower rate. So that eventually ends up creating a situation which means that even at times of low demand, there is always some demand. Demand never goes to zero at a country level. Yeah, there's always some demand, and it is really at least that level of demand which we tend to consider as the base load, as a demand that we always need to be there. And typically we try to cover that demand, historically at least, we have tried to cover that demand with power stations that are reliable, so they can be trusted to produce energy when we want it. And ideally, they're as economic as possible, simply because that's electricity that we need to produce all the time. We ideally want it to be as low cost as possible. Now, typically that demand has been covered by inflexible power stations. So power stations which are not particularly good with shutting down and starting up and doing start-stop operation, but rather with power stations that are low cost to run, but typically once they start running, you don't want to stop them and start them again. Then there's the opposing end of that, which is peak load, as we call it, and that is the type of demand that is fluctuating a lot, that is going both up and down during the day, and that requires different type of power stations to be served. Yes, so it requires power stations that are flexible, that can ramp up production fast, and they can lower the production again when the electricity is not needed, and manage to follow the demand and the demand's fluctuations during the day. So is that kind of clear so far as general principles? Does that make sense to all of you? Yeah, I'm not hearing any questions. So that's probably a good thing. Let me carry on with the rest of it then. So then with that in mind, I'm going to show you these graphs here. There's nothing very, very spectacular about these demand lines. They're typical demand lines for the UK. They're a bit old now, but the shapes are pretty much the same in various places of the world and in various countries. What I want you to see is what is the shape of the demand over a 24 hours period, over a typical 24 hours period for certain parts of the year. So we have 4 lines here. The lower one, the red one, is showing your summer minimum. So for that particular year, where we're focusing here, like I said, this is a little bit old. So for that particular year, we had a specific type of demand, a level of demand in a certain day in the summer that was the minimum level of consumption that we ever had in that year. So that's your red line. Then the green line is a typical summer period. So the typical summer is more demand because summertime might have higher or lower demand depending on the day and all of that. And then you will have a typical winter and then a maximum winter. Yeah. So you see that's the blue and the black lines. Just to be clear, are you all clear with why demand would be higher in winter and lower in summer? Or is anybody that doesn't think this is normal?
For heating.
For heating purposes.
Yeah.
So heating is one of the good reasons, and some heating relies on electricity, it's true. But we've been talking about before that most heating does not rely on electricity. Most heating relies on other things, right? Most heating relies on gas. So why do we see that crazy discrepancy here? What is it?
Light.
Lights is a very big one, correct? Other things? Any ideas?
Transportation.
This is about the UK, by the way. What you see here is the UK. Any other ideas? What might be causing that kind of discrepancy during the year? Because if you can see, the discrepancy is quite big. If you take, can you see my mouse cursor on your screens?
Yes.
Yeah, you see it, okay.
Yes,
so
yes, we can.
If you see, for example, now let's take the typicals, let's not go for the extremes. So for the typicals, for summertime, you have something like, what is this? Roughly 42, 43 gigawatts of demand, yeah, as maximum demand in the day. And for winter, that demand grows a lot more. It goes to something like 55, 57, something like that, yeah? So it's a significant difference. What's causing it?
Maybe because of transportation.
What is it? Say again?
Transportation.
Yeah. So you see, in many countries, during summertime, certain modes of transport, particularly urban transport, if you think of transport modes like, metro in the cities and things like that, they don't run at full capacity. Yeah, so they run with fewer trains. So that is another angle that might lead to lower consumption. So there's lower demand in transport. There is also lower demand from the industry, because summertime means pretty much everybody goes on holiday at some point. So that means that lots of factories might be operating with one shift less in summertime. So there will be, again, lower demand because of that. In wintertime, all of these things work a lot more.
Could it also be because people spend more time indoors?
Oh, please, can you say this again? I've missed it.
That people spend more time indoors than outdoors during the winter.
Correct. So all electrical appliances are bound to be used significantly more in wintertime. Yep, correct. Correct, that's another one. So the way for us then to think about it, I mean, of course, like I said, and I kept emphasizing before, this is for the UK, and it's a little bit old, so that's approximately 10 years old graph. The shape is not particularly different if you look at it today. What changes gradually is that while we're installing, I mean, even in the UK, we see a gradual increase of air conditioning installations. So what that does is that it increases the demand for electricity in summertime, because more and more places need to have air conditioning at summer. So it increases the summer demand a little bit. So you could see that happening. So as a result, there is not, I mean, the difference between summer and winter demand becomes a little bit smaller. If you were looking for such curves in other countries, if you were looking, I don't know, for example, in Greece, which weather-wise is very different from the UK, do you think the curves will be similar? Or what difference would you expect to see? As a speculation, I mean, you don't have it in front of you, but if you were to speculate, what would you expect to see?
I would suggest that in Greece, during winters, the electricity demand would be lower compared to the US.
Correct, to the UK. This is UK.
UK, I'm sorry.
Yeah, the US is very variable because it has all types of weather. So this is a good point. So when I was growing up in Greece, pretty much what I've known when I was, or not growing up so much, but rather, when I was initially working in these issues in Greece, the clear thing to me at the time was that Greece has a peak electricity demand in summer. So the peak demand in Greece was in summer. It was not in winter. And it was in summer because of air conditioning. That was the reason. We had a lot of air conditioning going on in summertime because it's necessary, because the temperatures are really high. So that was causing the highest demand you would expect in the year. And there was another peak, usually at about December time during Christmas, which happens in pretty much every country of the world, every country that celebrates Christmas, really. So these were the two peaks you would see in Greece. So even though very much like every other northern hemisphere country, Greece also in winter will need more lights, and it will have more factory shifts, and will have all of these things. All of these things were essentially surpassed by the fact that summer required a lot of air conditioning. So essentially that was driving demand higher than the winter demand. Yeah? Does that make sense to all of you? Is it kind of straightforward to understand?
Yes.
Yeah? Okay. So air conditioning and generally electric heating and electric cooling require a lot of energy. Yeah, it's more energy than lights, for example. If we were to compare these two, just for the sake of it, I mean, if I were to give you just a few numbers now for just, for very rough estimates, the lights in your room, do you know how many watts they are? You take a risk and say, roughly, if you have normal, modern lights in your room or LED lights in your room, how many watts would they be? Almost, approximately. You don't need to know exactly, but what do you think?
Around 10, maybe.
Around 10, yeah, correct, yeah. So maybe about 10, maybe 12, maybe 15, maybe 8, depends. If it's a strong light, maybe about 15. If it's a weaker light, maybe 5, 6 watts, yeah? So it's tiny. It's really, really little amount of energy. In contrast, an air conditioning unit for your room, how many watts would that be? Roughly.
600, I don't know.
Yeah, it's about 2,000, yeah? So it's about 2,000 watts. It can be 1,500 or 3,000, depends on the size of the room. But roughly 2,000 probably is correct for, for many types of rooms. So what I'm trying to tell you here is that, switching on lights in winter doesn't have an enormous impact by comparison to switching on air conditioning in summer. It's really a totally different level of magnitude altogether. It can be almost 1 in 1,000, the difference in demand there. Yeah, so this is what can totally change the patterns here. But the thing to also keep in mind is that many households, when they start having air conditioning units in a warm country, let's say in Greece, for example, when they start having air conditioning units which they use predominantly for cooling in summer, lots of these households will end up using them for heating in winter as well. So most air conditioning units can be used for both, yeah, for both heating and cooling. Not all of them are particularly good for heating. That can be a bit more of a challenge for them to deliver good performance. But for, let's say, if the weather outside is not ridiculously cold, if it's not minus 10, if it's just, plus 5, for example, then they can probably deliver a decent amount of heating in winter. So for Greek winter, for in Athens, for example, the big cities, this is adequate. So in that sense, you might see air conditioners increase the demand in summertime for cooling, but they might also increase the demand in wintertime as well. Yes, it can be a balanced approach between the two seasons. So that's just some broader considerations, just as broader understanding of how these things work. Any questions to that point before I get to a couple of other observations here? No? All good? Sure, yes.
Do you see any changes in the trends nowadays that the houses are more, let's say, energy efficient?
Well, not so much, because the issue with household energy efficiency is that it is mostly an issue for new built houses. So new built houses, depending on the country you're at, but they can be a lot more energy efficient. This is true than in the past. However, we do in most countries, we don't do enough to retrofit old houses with more energy efficient features. In Central Europe, there is a lot more happening. In the UK, things are horrendously bad. I don't know how many of you have had the pleasure of staying in old British houses. They can be really, really bad in terms of efficiency. As one of my former PhD supervisors used to tell me, he was saying that one of the problems with the housing stock in the UK is that in the UK there are no earthquakes. So as a result, houses tend to stick around forever. So we have Victorian houses. The first house I used to live, the first house I bought actually here, a few years ago, was an old Victorian house that was built in 1875. Yeah, that was it. It was a normal house on the street. Everybody in my street had a house that was built in 1875. And it was kind of okay. It was standing. It wasn't moving very much. But it's old. It's very old. So trying to make a house like that energy efficient, good luck. There's no easy way. You can do a lot of things to improve it. You can, change the windows, make them double or triple glazing. but you always struggle with how to bring it up to speed, because the house itself, the main, the walls of the house have no insulation. There is nothing. It's just bricks, just brick wall, nothing else. So there's very little you can do. You can just you have to rebuild essentially the house, like you build a coat outside of your house in order to insulate it. It's really difficult, and it costs a lot of money. And energy is not so expensive. It's not expensive enough to justify this thing. So if you have a house of that sort in the UK, you might need 15,000–20,000 pounds to insulate it. That's a lot of money. I mean, you will never make that money back from heating bills. It takes 50–60 years to make that money back, by which time you will need to redo it again because it's probably going to have collapsed already. So energy efficiency improvements in houses is a bit of a difficult one. It's a bit of a difficult one because we're not retrofitting houses fast enough. And okay, that's the UK's story. Other countries are a little bit better. But I think it's probably one of the most difficult areas in terms of energy use improvements. Yeah, does that cover you? Does that make sense?
Yes, completely.
Yeah.
Thank you.
Yeah. Any other questions? Okay, on additional points on the last topic. Sorry, go ahead.
Does the mass tourism in Greece contribute to the increase in electricity demand in the summer?
Okay, wait, I've lost that completely. Let me have you saying it again, please.
Does the mass tourism in Greece contribute to the increase in electricity use in the summer? Is that like
Correct. Yeah, that's quite a significant one for a country like Greece, that it takes something like doubling its population in summertime. That is not trivial at all. So essentially what you have is places which are touristic destinations. Think, for example, I don't know, the islands or so. In some of these places, the population rises 10 times. Yeah, you have islands that normally in winter time, they might have, something like 200, 300, 400 people. And suddenly in summertime, they have 5,000 people, which means 5,000 air-conditioned rooms that didn't exist before. So that can have an enormous impact in places like Greece, and not only Greece. I mean, I'm sure Italy is very similar in that regard, because there's a lot of tourism visiting around, and not just Italy, all the Mediterranean countries have that. So yeah, that's a good observation. Well done. And you can imagine, of course, what's happening. One thing is to consider the country overall, where you might have a doubling of the population for a certain period of time in summer, but it's a completely a much more intense story if you were to think what's happening in certain hotspots of tourism, where it can easily go 10 times up. Imagine what's happening to infrastructure there. What kind of electricity cables you need to be able to accommodate that. It's not easy, particularly for Greek islands. It's quite insane because most of them rely on their own power stations. Most of them are not connected to the Greek mainland, so they have their own power stations that have to be able to cope with that. It's one of the main challenges with electricity production in Greece. So yes, so that's that. Are you all clear to that point for what we said so far? Are you comfortable with all of that? Yep. Okay. So let me take you to another observation, a final observation here. That is, this is the hours of the day. So what I want you to take a look at is a little bit on when does peak demand happen. So typically, peak demand happens if you look a little bit in winter, because that's a little bit more typical for most places. So we start seeing a significant rise in winter during the late afternoon hours, yeah? So from something between, say 4:30, thereabouts, until maybe about 7:30, 8:30, something like that. It's this area here, yeah? This is what is one of the trickiest times in the day for electricity demand. And then it gradually falls as the night comes, people go to sleep, so a lot of the types of consumption just are eliminated. And then it begins the next day again, keeps falling in the first morning hours until people start waking up. Yeah, so at about 5:30 thereabouts, when the first people start waking up, then the early risers, it gradually picks up quite fast, stays about there during the daytime, and then rises again in the late afternoon. Yeah, so that's the pattern that repeats in many places, in most countries. That's the kind of pattern that you have. We will be revisiting this pattern because what we'll realize is that we can play a lot here. Yeah, if we could be storing energy during the day, using it at other times, if we could storing energy during the night, even at the hours where demand is very low, could we be storing energy then and then using it during the day? So imagine whenever you see these patterns changing, don't see them only as demand changing, see them as price of electricity changing. So in some places, demand during the late afternoon hours, like around here, where I'm showing you now, can be about 6 times more expensive. So electricity in these hours can be up to 6 times more expensive than it is during the night. Yeah, so that's an insane amount of price differential, 6 on 1 for different times of the day. Which if we could materialize, could we be charging something during the night for 1 unit, for £1, and then selling it during the day for 6? That could be interesting. There's a lot of money to be made there. So these arbitrage opportunities are quite important for us to think of. They're also quite important for us to think of because renewables generate energy pretty much randomly. Yeah, they can generate energy now that you need it, in the afternoon, or they might generate all their energy in the nighttime that nobody needs it. If it's wind energy, for example, it can happen throughout the night. The wind blows quite well. Nobody needs that energy at that time. It's not relevant. So we need a way to store that energy to be able to then use it during the day. So these are considerations for us to keep in mind. I'm not going to go into a lot of detail now with them, but I'm just making sure that you have them in your mind as issues that we will need to think solutions of as we go on. Yeah, and we understand what types of energy are available, what types of technologies are available. So for one last time on these ones, do you have any other questions, any queries on what you see? All good. Doesn't sound like you have any. So let me take us then. Oh, it looks like I'm in the darkness here. Yeah? Okay. Let me switch on my light. Okay. So let's carry on then. So let's think a little bit of the electricity supply chain very briefly. It has a number of angles on what's happening into this supply chain. So we have a generation, so that is power stations. And here are coal power stations, a wind farm or a nuclear power station or a solar farm or anything of that sort. Yeah, anything that produces energy at a significant scale, that I would call a power station. So that's the generation level. And then from that level, we need to take the electricity at relatively high voltage and transmit it with these high voltage cables to closer where the consumption is. Yes, so we normally generate electricity in places wherever it's convenient to generate electricity. That's not necessarily very close to where we consume electricity. Yeah, so these places might be different, the place that we produce and the place that we consume electricity. So quite often electricity needs to be transported to relatively high distances, very significant distances. And our main concern when we do that is to reduce losses. So electricity, when it's transmitted through cables, causes significant heat losses. This is not necessarily, it's you cannot eliminate losses. Losses are always there. You cannot make them zero. But there are certain ways in which we can reduce them. And the typical way with which we do that is when we have our transmission cables running at high voltage. That allows us to reduce the transmission losses. So this can be voltage, as I say here, like 765 kilovolts or other rates of voltage I'm outlining here. You don't need to remember those numbers, don't worry too much. It's just for your own reference. Then as soon as electricity arrives in front of an urban center, in front of a city, then we normally have another small station where we change the voltage again and we make it distribution voltage level, which is essentially typically can be 26 or 13 kilovolts or all the way down to 230 volts or 240 volts, depending on the area you are at. So that's quite important to understand, because there are different voltages in which we transmit electricity. The urban centers, the distribution systems run at low voltage, and they come all the way to your doorstep at a voltage that you are actually using at your property. Transmission is a lot higher, and it's essentially designed to run the long distances within the country. Then as soon as it arrives at your door, another part of the supply chain is your retailer. The retailer isn't necessarily some part of the physical infrastructure, of the actual infrastructure that you have there. The retailer can be just a company that essentially you are in touch with as a customer, and it's the company that sells you that electricity. It's not necessarily a company that does any of the above things. So a retail company might not generate, might not transmit, or might not distribute energy. It might just be buying energy from the distribution and selling it to you that you're the customer. So it can be just another level of the supply chain. It doesn't have to be somebody who does any of the previous things with the physical infrastructure. They still have a role to play. I'll explain a little bit about it as we go. So if I were to have you thinking a little bit for a minute, why do we have power stations far away from consumption? Why can that happen? It doesn't always happen, but it happens very often. Why is that the case?
Maybe for security or safety.
What do you mean? Say more.
Well, maybe some power station can have some problems, and with all that power involved, it can be translated into some real problem for the population that lives nearby.
Okay. It can happen. It can happen. It's not very common, but it can happen. Unless you're talking about a nuclear power accident, which is a whole other story, in which no distance is going to save you. But okay, there are distances that can save you, surely, but it can be more tricky there. Other reasons? Other reasons, anyone?
Maybe if we take the example of a, hydropower station, of course, we have to understand where resources are located, so we cannot put the power station everywhere.
Correct. You see, that was a very good example we just said, because what's happening is we will build the power stations usually where the resource is. So that's very true, of course, for renewable energy sources. So not all places have, a river or a lake or the geography to build a hydropower station that is very location specific. Equally, when you're building a power station that will run, for example, on coal, you will try to put it close to a coal mine. So wherever it is that you are digging for coal, you don't want to be taking that coal and transfer it with trains across the country. You want your power station to be nearby, yeah? So that's where typically most power stations have been located. It's a lot cheaper to transfer electricity with cables than transfer coal with trains across the country, yeah? So it's where the resource is. That's where we have the power stations. And then, of course, consumption will be in areas that have, developed industry at industrial clusters, or it might be in urban centers, in cities where lots of people are. So that is the reason why quite often we have very different locations between where production and consumption of electricity will be. So that's why we need to transfer electricity. And of course, with how a significant part of the renewable energy sources is being developed, that is becoming sometimes even crazier. When we have offshore wind farms, this can be very far from the coast. So again, we need to be further out, have longer distances, a lot of cabling in order to bring that electricity back onshore and close to consumption. So that's that. Let's. Is it clear for you all of that? Does that make sense, or is it confusing for anyone? All good? Okay. So let me go then to why do we change voltage? And here you will see a couple of numbers, which don't panic. It's going to be my most, my deepest dive to engineering, to engineering and physics here. So don't worry, I'm not gonna carry on with that stuff so much. It is just to show you a little bit. It's only for your reference. Just to say that in electricity, you will be encountering quite a lot of discussions about AC and DC. So apart from a popular rock band, it's the alternate current and the direct current. And like I said, don't panic if these things are totally new to you and you don't understand what I'm talking about. So most electricity generation is produced as alternating current. Yeah. And the electricity that you have at your house, the one that comes to your sockets at home, it's almost always AC. It's alternating current. Very rarely you have electricity seen in properties as DC, as direct current. Now, what is quite interesting is that many of our appliances are designed to use direct current. So for example, your computer, your laptop, uses direct current. Pretty much all microelectronic appliances, your computer, your phone, your TV set, or all of these will use ideally direct current, which they convert. They have a transformer. They convert to that direct current. Now, some types of energy, for example, solar panels, produce direct current. They don't produce AC. They produce DC. When you charge a battery, that battery stores energy, which then releases as direct current. Fuel cells, the same. They produce direct current afterwards. So it's quite an interesting world there, where both AC and DC need to exist. Now, that's just something like a reference point, because you will probably be seeing it in your reading. When you start reading for your coursework, you will see references to that. So that's why I'm mentioning it here. So for those of you who are not familiar, that you see it first time here rather than in random reading. Now, one thing for us to think of about what happens with the voltage and all of that, so is hidden in these equations here. So one way to think about the power we're transmitting through cables is that this is essentially a multiplication of current and voltage. So if you multiply the current and the voltage, that's how you get the power that you have transmitted. Now, an interesting detail here is, if you were to increase the voltage, like we said before you do, yeah, for the transmission cables, we said that you increase the voltage quite a lot. So you take that voltage, which is super high. So if you were to increase the voltage here for the same amount of transmitted power, it means that you could reduce the current, right? So you could reduce the current, increase the voltage, and still have the same amount of power transmitted. Now, if you would estimate the losses that you have from those cables then would have the losses, which are essentially a multiplication of the resistance of the cables, which is a specific property of the cables based on the material they're made of and the temperature and so on, multiplied by the second power of the current. Now, if you've made every effort before to reduce the current, that means that you're making a very significant progress with reducing the losses. Yeah, it's a squared impact, what it has. Does that make sense to some of you? Or are some of you completely lost what I'm talking about? Or does it, or is it clear? I need to say that there's no need to worry too much about it, because if you don't, I mean, it's as much engineering as I'm going to tell you about in this program. Okay, so I'm not hearing any questions, so probably you're all happy with it. That's good. Or you have just given up trying to get it. So that's, I'm not sure that's good, but anyway, if you have any questions on these things, let me know later on. So let me carry on then. So typically we will have, I mean, most of the transmission around the world is happening with alternate current cables. Some of it starts happening over the last decade or so with high voltage direct current. You will also see some of that in the literature when you're reading. So we often have large distances electricity being transmitted with HVDCs cables. Don't worry too much about that. There are questions about reliability, questions about maintenance. They're very expensive. Typically, they do have very low losses. So when you have large distances, often these cables are what is seen as the future option. These things start being important when you start thinking of large electrified regions that have a lot of penetration of renewable energy. So for example, if you start thinking of all Europe becoming one energy market with a lot of potential, a lot of capacity to transmit electricity from place to place, then that is where you need to start thinking of a lot of these cables becoming necessary. So it's not anymore about electricity being transferred, I don't know, from Veneto to Rome. Yeah, that's not anymore the question. The question is, can you transmit electricity from Norway to Italy? So that's going to be when it becomes a little bit crazier, when you need such distances to be capable of transmitting a lot of electricity. So we will be seeing gradually, what solutions are necessary and what can be done about them. So, like I said, I don't want to get into too much technological stuff at this point, but let's carry on a little bit. So, typical attributes of electricity that I want you to be thinking of. One is, we normally have big distributing generation facilities that will cause air pollution, that will cause climate change, that will overheat nearby water resources. They might have visual, they might have noise impact, and so on. Yeah. And when it comes to distribution and transmission, these again can be very big pylons that they carry cables over long distances. Very often these are located, within natural areas, forests or natural parks, and that's not necessarily the best thing to see within a natural park area. So people might not like them and so on. Yes, so there are all of these concerns there. But generally speaking, large-scale electricity, which is really, an important part of our electricity networks, can be annoying, can be there for people to see and people to comment on and people to have an opinion on. Important tricks to think of is that electricity is not easy to store. It's not impossible, but it's expensive and it's technically challenging to do at significant quantities. So that's something that defines very much the nature of dealings we have with electricity. So that means essentially that we need to be matching production and consumption non-stop. It's a non-stop game that we need to be able to do that. And small disturbances can have enormous consequences with blackouts. So it doesn't take a lot of a disturbance of this balance between production and consumption for an electricity grid to go off and fall. So that's on that matter. Any questions so far before I move on?
No.
Was that a no? Or did you say something else? Sorry.
I see. No.
Okay,
I
okay.
don't have any questions.
Okay, beautiful. Okay, no problem. So, if all of that up to here is clear, let me get you a little bit to the trade part, and I will not expand now very much on trade. We'll have a lot more to say later on, but it's good to give you a feel of what's happening on the trade aspect of it. So, we have different ways in which we break down the electricity industry. Now, in the past, I'm thinking now, say 20 years ago, 30 years ago, electricity was pretty much a state monopoly. In most countries, it was one company or maybe a couple of companies that were running electricity generation, and they were responsible for all the country. Regardless of which country you were talking about, that would be the case. Now, gradually, this has started changing. So in the past, when that kind of market design was available, of course, that was not even a market. Yeah, there was not even a trade. It was one state monopoly, one company that was controlled by the government, and that company had the responsibility to produce energy and make it available for people, and that was it. And the main, really, let's say, characteristic of that was it would try to make, best use of indigenous resources. It would try to reduce costs, and so on. And it would also try to require a little bit to be based on indigenous resources that would be, again, usually state-controlled. So that was the state monopoly sort of design. Gradually, we started moving away from this type of designs. Why? Because we tended to have a feeling that the private sector can do everything better. I'm not saying that this is absolutely true or that this is absolutely rubbish. There are cases in which privatization has indeed done better, and cases where it hasn't done much better. So let's move on and see a little bit what's happening here. So when it comes to privatization of electricity, we have had a number of things happening. So one of them has been that private companies would start operating the generation utilities. So these are the power stations, the facilities that generate electricity. And often you would then have private or state companies that operate the transmission grid, so the high voltage grid. In many countries, even if they have privatized generation, the transmission grid, it is still controlled by the state. Not in every country, but in many countries it is still state controlled. And then you might have more private companies involved in the distribution network, and definitely private companies handling the retailing aspect of it. Now, with oversight on all of this, usually you will have an independent authority that regulates the market. So, and sets out the rules for competition and so on. So typically, that is a standard design in most privatized and liberalized electricity markets. Are you familiar with that at all, that design, or have you seen it again previously or not?
No.
Not very familiar. Okay. Okay, let me think a little bit how I get you to that. So there are a couple of aspects on this one that I want you to pay attention on. So one is, when it comes to electricity generation, can you have competition, you think, between companies? Could it be an area where competition exists? Are you familiar with competition economics at all? Have you done any of that, competition economics?
Yes, a bit.
Yeah,
maybe
you must have. Those of you that have economics degrees, you must have, yeah.
Yeah, maybe it depends on who owns the resources. So yes, I think yes, in generation can be a competition.
Yeah, it is doable. Yeah, I mean, if there is an opportunity for new entrants in the market, then private companies that own generation assets can enter the market, and they can compete with each other. They can each one of them try to offer a lower price or a better service or whatever, and compete with each other. So it kind of makes sense. Then when it comes to the transmission grid, that is where you typically cannot have competition. And the reason is because there's no incentive, there's no need to have multiple transmission grids. Yes, so you typically, in one country, you need one transmission grid. You don't need many different cables going to the same direction. So that's when things are a little bit, irrelevant. So competition there is not exactly a thing that can happen. So this is essentially what you have as a natural monopoly in these places. When it comes to transmission, that is, in most countries, that is seen as a natural monopoly. And as a result, you will be running that by a state company or a private company, but that company would be extremely highly regulated. Because it's a monopoly by nature, that is the type of the area it works in, it will have to be very highly regulated so it does not abuse its power. Then when it comes to distribution, so that is the low voltage cables. Again, with these ones, in no city you're going to have two different companies putting cables on the ground to reach your house and having more cables with a different company to reach your house. It is doubling all the resources, doubling all the infrastructure for no good reason at all. That's very expensive infrastructure. So no company would come in and do it twice. It's stupid. So again there, even though you have usually private companies running distribution networks, again, these are natural monopolies. If I give you a different example of that, let's think a little bit about trains. Yeah. So you have the trains. Now, trains, they have two parts, really. Two at least parts, the train network. So one thing is the lines, the railway lines, and the other thing is the trains. So if you think for a minute about the train lines, that's like the network, that's like the electricity network. There's no point having one line going from, say from Bologna to Venice, and a second line or a third line going from Bologna to Venice directly. That would be stupid. Why would you have so many lines? Essentially, you need one line, and if companies are going to compete, that should be competing with their trains. So they should be using the same line, but competing with having different trains running on that line and running faster, more comfortable, or having better service, having better air conditioning in the wagons, or better prices for their tickets and so on. So the competition would be at that level. It's the same with electricity. When it comes to the cables, there is very little scope for competition on cables. Where there is scope for competition is for the production. Can you produce energy in different ways? Make it cheaper, all of that, yeah? Or when it comes to retailing, can you offer your customers better service? Can you offer your customers better prices or better packages for energy for them to want to be your customer? So this is where there are certain areas where competition makes sense and there are certain areas where competition doesn't make sense for electricity. So I hope that helps explain it a little bit, where it could be a natural monopoly and where it's actually open for competition. So in the UK, for example, you will have something like 10 companies generating electricity, a little bit more, but 10 significant companies generating electricity, and you will have regional distribution companies. So these are companies which are essentially, if you imagine the country is split in certain areas, in 11, 12 areas, which have distinct grids, distribution grids, and you have one company distributing energy per grid, per region. Yeah, so every region is having a natural monopoly. And then you have several dozens of private companies handling the retailing. So that is roughly 65 companies right now in the UK doing electricity retailing. Like I said before, most of these companies don't generate, don't transmit, and don't distribute energy. They just retail it. They just buy it from somebody else, from a wholesaler, and they retail it to individual customers. So that's how that system works. Is that all clear for you? Does it make sense? Are you happy with it?
Yes.
Yeah? All good then. So let me take you to the next bit. So those of you who have seen before competition economics, you will know things like horizontal expansion and vertical expansion. The same things exist in electricity. So you will have things like horizontal expansion, where a company expands, for example, its generating capacity. So when a company, imagine, essentially has more and more generating assets in a certain market. So that can be a situation where a company, for example, controls 100% of the generating assets in that market. So it's essentially a monopoly. Yep, it can happen. Of course, it can happen. It's not desirable. I mean, it wouldn't be a competitive situation, but that would be the result of a company expanding horizontally. So that's one situation. And of course, it's not desirable from a competition standpoint. The other side of it is the vertical expansion. So that's when a company produces energy, so it's on the generating side, which then has the capacity to transmit or distribute or retail. It can happen as well. So that will be a vertical expansion. That's where a company goes for all the supply chain, so from generation to transmission to distribution to retailing. Now, what we normally have throughout the world that has liberalized and privatized electricity systems is that competition rules will discourage horizontal or vertical integration and expansion. That is not something that is desirable. Neither of the two are desirable. Yeah. Let's see a little bit. Why are they not desirable? So let's think. So the rules in more detail normally would say that companies which generate electricity are not allowed to transmit it, or companies that transmit electricity are not allowed to pay in the generating side, or companies that are distribute energy, they should not transmit energy, or companies that retail energy shouldn't be allowed to distribute that energy, and so on. So no company is allowed to have control of two continuous segments of the supply chain, if you see what I mean. That is the main concern. Why do you think these rules exist? Why do you have these rules?
To prevent from monopolies.
Sorry, there was a lot of noise. Can you say it again?
To prevent from monopolies.
To prevent monopolies. Is what you said?
Yes.
Yeah. Okay. Yeah, it's very true. Yeah, to prevent monopolies and the power abuse that comes with it. Yeah. So imagine if a company, for example, distributes energy and then retails energy. There's always a danger that it will prioritize the energy that it distributes in the retail market. Or if a company produces energy and then wants to transmit it, it might, for example, create obstacles for other producers, and it might always prioritize to transmit its own energy and not the energy of other competitors. So these are the dangers that are actually very valid and can happen. So that's why these rules exist, and that's why we need to see competition amongst all of these stages. The view is, the economic view of competition economics really, is that competition is good for the customers. So if companies are obliged to compete with each other, then they will have to improve their services, they will have to improve their offers, they will have to improve their financial offering, eventually benefiting consumers. That is the idea. So if you force them to do that, then that's going to be good news for the consumers. That is why competition rules exist, to make a little bit life difficult for companies, and as a result, create a situation where consumers are being benefited by that. So that's the principle of competition economics. Now, in reality, a lot of things are happening. Yeah, it's not just one thing that is going on. In reality, companies tend to be involved in various parts of systems that they're involved in. For example, in the UK, that is a very liberalized market and a very privatized market. What we have is that several companies that are involved in generation, they're not involved in transmission, they're not involved in distribution, but they are involved in for example, retailing, which is fine because from generation to retailing there's a big gap. So they have little control over the supply chain, over what's happening in between these two levels. And that's happening quite a lot, and they still control significant parts of the market for that reason. And in other countries, you have things like, for example, specific companies controlling distribution and controlling also retailing, which can be, again, quite tricky. It's not always that good for competition when these two happen in the same market, but particularly that bit is happening in a few markets. So that's another consideration that is going on. So if you are happy with all of that, are you happy with all of that, or should I take you to the next slide? Or are you just dead tired and you cannot respond anymore?
No, it's fine.
It's okay. It's okay.
Have I exhausted you?
Okay.
No, don't tell us anymore about electricity trade. Okay, so I'll show you a slide here. It's really for group work, and I don't think we'll manage to do it right now. But it's just to give you a glimpse of what we're going to do when we start on Monday next week. So that is, we will form small groups, and actually I will play with teams right now to see if I can use the breakout rooms the breakout rooms function, because I haven't used it before, so I want to see if it works well. So we'll break out in a number of small groups, and each group will choose one of the companies that you see here, or I don't know, if you're very keen, you can choose another company, I don't mind. And then within your team, you will have a conversation about what that company does. So we'll ask you to go online and figure out what that company does and what kind of activities it takes up. These are electricity sector companies. These are large electricity sector companies, what you see here. So within your group, you'll have a conversation using online resources to take a look and see what these companies do, what kind of stuff are they active in, what is their business. And then I'll ask you to come back and say a few words about what you found out for your own companies, yeah? So probably that's going to be, maybe we'll change the timings here. Maybe it's going to be more like 20 minutes for your research and maybe a couple of minutes for presentation. But that's going to be our first activity once we come back on Monday. What I want to do before you guys go, I know it's only 5 minutes, and sorry, I'm going to have to use them. What I'll do now is I'll stop sharing my slides, and then I'll try to run the automatic feature of breakout rooms. Let's see if that's going to work. So if I say I want, how many are you here? You're 56. If I say I want, for example, 10 groups, and I want this to be designed automatically, let's see if it's going to work. Can anybody hear me?
Yes.
Yeah.
Yes.
Can you all hear me?
Yes.
Yes.
Yes, we didn't get any notification.
Ah, because I can see the rooms here. Can you see the rooms, or it's only me that can see them?
No.
You cannot see anything?
No.
Okay,
No.
that's interesting. I think I know what I should do. So I'll press the button that says assign participants. And I think what that's going to do is it's going to take you to the rooms. When that happens, probably that's going to be the time when you cannot hear me anymore, that I will need to come to individual rooms for you to hear me. Let me see if that's the case. I'll do that. And hopefully then I'll find a way to bring you back and say bye-bye. Okay, so let me see if I can manage it. Is anybody moving to rooms or not yet?
Not yet.
No.
I think I'm failing.
I think we're all here.
I think I'm failing miserably here. Let's see. Is anybody disappearing, going to rooms?
Yeah, it seems that we are.
Yes, it works. So it seems that some of you are in rooms. Can you hear me? Can you still hear me? Maybe. Can anybody still hear me? Yes, okay. But I think that's because you are not allocated in a room, I think. I think those who are in rooms, they probably cannot hear me anymore. So then another question is, how do I go to these rooms? Georgia, you should have been moved to your room automatically. So I think maybe the time that the allocation happened was a time when you were not connected, I think. And then you joined the chat a little bit, a second afterwards, and you were not allocated when the allocation happened. But don't worry about that. Normally that should be a bit more smooth next time. So let me see. So I'm closing here. So I'm closing all the rooms now, which will probably bring back everyone. So now you're all coming back.
Yes.
Yeah, hopefully. Okay, and some of you have cameras on. Wow, okay. I see some masks on because you're in the library. Well done. So when you were in your own rooms, could you hear me?
No,
No.
just
No.
the
No.
But so, and you were, I don't know, 5 or 6 in every room, and could you hear yourselves?
Yeah, we can hear
Yes,
each
yes,
other.
yes.
Yeah? Okay. So then we can use that to do group work next time. So the thing I need to find out how it works is whether there is a way for me to be visiting your rooms and helping you out in your work while you go on. Okay. I'll have to research on this a little bit. I have a few more days to find out how to do that, because it's easier to do in other platforms. On Teams, I don't think it is that straightforward, but I'm going to find a way. It's going to be straight. It's going to be easy. So with that said, thank you very much for attending today. If you have any questions, anything you want to clarify further, drop me a line. I'll do my best to respond. Until then, have a good time. I'll see you on Monday.
Thank you.
Okay,
Thank
bye-bye.
you.
Thank you,
Bye.
Professor.
Thanks, Professor. Goodbye.
Thank you. See you as soon as. Bye bye.